Welcome to the Chapter 7.2 lecture on Laplace transforms, Part 2. So last time we learned the Laplace transforms of a number of functions, such as the Laplace transform of 1, t to the n. Well, we did t, but it generalizes for t to the n, e to the at, sine and cosine. And there are also Laplace transforms of hyperbolic sine and hyperbolic cosine, which can be useful. And the hyperbolic sine of x is simply e to the x minus e to the negative x all over 2 by definition. And the hyperbolic cosine of x is e to the x plus e to the negative x over 2. And you might notice the similarity in the Laplace transforms of sine of kt and hyperbolic sine of kt. For example, the only difference is that plus versus a minus. Likewise, for the Laplace transform of cosine versus hyperbolic cosine, it replaces that plus with a minus. And what's going on there? Well, the cosine of ix turns out to be the hyperbolic cosine of x, as one can find by plugging ix into the Taylor series for cosine, and then gathering terms in the appropriate way. It will turn out to be e to the x over 2 plus e to the negative x over 2. They have equivalent Taylor series. And similarly for hyperbolic sine, it's I sine of ix. So the reason for this similarity is that if you replace k with ik, well, I squared is negative 1. So in other words, ik squared is negative k squared. So that kind of thing is behind, intuitively, the similarity. And regardless, these will be useful, not because we'll be dealing with differential equations involving hyperbolic sine and hyperbolic cosine, but in finding inverse Laplace transforms, so in other words, undoing it. And that is the topic of today's section, in part, is the inverse Laplace. So the inverse Laplace transform is simply the inverse function. So for example, the Laplace transform of 1 is 1 over s. That means that the inverse Laplace of 1 over s is 1. Laplace of t is 1 over s squared. Inverse Laplace of 1 over s squared is t. We will be solving differential equations by taking the Laplace transform of both sides and then undoing the Laplace transform after some algebraic manipulation. And that is where these guys will be useful. We might wind up with an expression like this. And then undoing the Laplace transform, we would get hyperbolic sine of kt. And then we can just use this definition to get it in terms of our regular functions, e to the x and e to the negative x. And recall that the Laplace transform is linear. It distributes over sums, and you can pull out constants. The same thing applies to the inverse Laplace transform. In fact, the inverse of any linear function is also linear. And this will be quite useful in evaluating inverse Laplace transforms. Let's do an example. Let's find the inverse Laplace of 1 over s to the 4th. And the idea behind finding inverse Laplace transforms is to look at our list of known Laplace transforms and identify an element that looks like what we're given and manipulate what we're given to look like that element. So in this case, 1 over s to the 4th, that looks like, well, it's a constant like n factorial over s to the n plus 1. So the idea is we'll write this first as 1 over s to the 3 plus 1, and we increasingly want to make it look like this. Okay, so s to the 3 plus 1. But to make it look like that, we want an n factorial up there, where n now is 3. How do we do that? Well, we actually just stick it up there and then divide by it, which is doing nothing in a fancy way. And doing nothing in a fancy way is what mathematicians are best at. As a joke. And now we can use the linearity of the inverse Laplace to pull out that 1 over 3 factorial. And the point of these manipulations was to get it so that we are taking the inverse Laplace of something that looks exactly like one of our known Laplace transforms. And now it does. So this is 1 over 3 factorial times t cubed. And 1 over 3 factorial, that means 1 over 6. So the inverse Laplace of 1 over s to the 4th is 1/6 t cubed. So remember this trick where we can always put a constant inside and then divide by that same constant to do nothing and not transform what we're doing. That's a very powerful trick that we'll be doing a lot in finding inverse Laplace transforms. Let's do another example. The inverse Laplace of 1 over 2 plus s squared. So look through this list and think, which one does it look like? If you think it looks like sine of kt, you are right. K is a constant. So this is a constant over 2 plus s squared, constant over s squared plus something squared. It looks something like that. So we'll manipulate this and make it look increasingly like that. So first, s squared plus 2. We want it to be s squared plus k squared down there. How can we do that? Well, we'll write that 2 as root 2 squared. Okay, making progress toward making it look like that. Now, we would need a k up there. How can we get a k, which in this case is root 2, up there? Well, that same trick as before. We'll just put it up there and divide by it at the same time so that we're not actually changing anything. And now we can pull out that constant. And now we have manipulated it to look exactly like this. So this is 1 over root 2 times sine of root 2t. So go ahead and try your hand at this. Pause the video, try to find the inverse Laplace of this function. Okay, so first we look through at what this looks like. It looks like the only viable option is 1 over s minus a. That's 1 minus s down there. First, let's pull out that constant. So 2 times the inverse transform of 1 over 1 minus s. Now, this is s minus a. This is 1 minus s. So we need to somehow switch these two. How can we do that? Well, remember that we can always swap 2 by pulling out a negative. So this is negative 1 over s minus 1. If you distribute that negative back inside, we'll have a negative s plus 1, which is 1 minus s. Now we can pull out that negative sign. And now we have manipulated it to look exactly like this. So therefore, the inverse Laplace is e to the at, which is e to the 1t in this case. So we have negative 2 e to the t. Now, sometimes we'll be given more complicated expressions, and we need to break it up into 2 simpler expressions, each of which looks like one of our known Laplace transforms. So 1 plus s over 1 plus s squared. So down here, we have a 1 plus s squared that looks something like the denominators of the Laplaces of sine and cosine. Up here, we have a 1 plus s. If we separate this into 1 over 1 plus s squared plus s over 1 plus s squared, then this guy looks like sine, while this guy looks like cosine. And the Laplace inverse is linear, so we can break that up into the 2 pieces. Okay, so now that guy is this guy, and this is that. So this is simply sine of 1 times t, to be perfectly precise. Perhaps we should note that that 1 is a 1 squared. So this is s squared plus 1 squared, s squared plus k squared. It is of these forms. So that's sine of 1t plus cosine of 1t. So the inverse Laplace of this is sine plus cosine. Now, sometimes we need to do partial fraction decomposition to break it up. I'll illustrate this 2 ways. First, with partial fraction decomposition, if we don't want to deal with hyperbolic sines and cosines. So if we factor this, that is 1 plus s times 1 minus s. And we can do a partial fraction decomposition in which it decomposes in this way. It's going to be a over 1 plus s plus b over 1 minus s for unknown constants a and b. And we can solve for a and b by recombining them and equating coefficients. We've done that a few times in this class at this point. In particular, we did partial fraction decomposition back when we were doing nonlinear modeling. And I'm going to show you a shortcut. So for simple partial fraction decompositions, one can kind of fudge one's way into it. So when I see this problem, I think, okay, if I put a 1 plus s up there and a 1 minus s over there and add them, I'll get a 2. So I think maybe a 1/2 and 1/2 will work because 1/2 times 2 is the 1 that we want. And indeed, 1/2 times 1 plus s plus 1/2 times 1 minus s is 1. So it does decompose in this way. And then we can separate that using linearity in this way. So that's distributing the inverse transform over the sum and then pulling out the 1/2 from each, since we can pull out constants. And now each of these almost looks like 1 over s minus a. Here's what we had. And to get it to look like 1 over s minus a, we need to put that s first. So how do we do that? We pull out a minus sign. So that's negative 1 over s minus 1. And over here, 1 plus s, let's write that as s plus 1. Okay, so here we pull out that minus sign and we're good to go. 1 over s minus 1, 1 over s minus a. Over here, 1 over s plus 1. Can we make that look like 1 over s minus a? So here's another common trick. S plus 1 is s minus negative 1. So there we go, that's 1 over s minus a. So now it's of that form. So this is negative 1/2 e to the 1 times t plus 1/2 e to the negative 1 times t. So we have found the inverse Laplace of this function through that partial fraction decomposition to split it up and then dealing with each part separately. Now I said I would show another way, and that other way is using hyperbolics. So k over s squared minus k squared, the inverse Laplace of that is hyperbolic sine of kt. And these are easy to reconstruct. If we put a h there for the hyperbolic, all that does is it makes that plus sign into a minus sign. So 1 over 1 minus s squared, that looks like k over s squared minus k squared. We need to pull out a minus sign. Now it's 1 over s squared minus 1. Let's pull out that minus sign. And we have negative inverse transform of 1 over s squared minus 1. But 1 is 1 squared. And now that is the Laplace of hyperbolic sine. So this is simply negative hyperbolic sine of 1 times t. And hyperbolic sine, remember, that is e to the t minus e to the negative t all over 2, which is e to the negative t minus e to the t over 2, distributing that minus sign. And that is the same answer we got via the partial fraction decomposition. Now I want to show you something. If you go to modules in the canvas and go to Laplace transforms, then right here is a table of Laplace transforms. Click on that, and it has all of these ones that we talked about and then more. So for your various right-hand sides, or various forms of them, you can quickly find the inverse transform. So if you have something of this form, for example, there is the inverse transform of it. And indeed down here, these are the hyperbolic sine and cosine that we've talked about. They're all there, nice and handy. And then if you forget the definition of hyperbolic sine and cosine, just go to the Wikipedia page, for example. It's easy to Google, and it's right there. Hyperbolic sine is that. There's hyperbolic cosine. So you can then convert them into our ordinary functions. All right, so either way, in some cases, partial fraction decomposition will be unavoidable because even that big table won't have some of the more complicated ones and we'll need to do a partial fraction decomposition. Okay, and here is an example of one where this is definitely not in the table. So here, no matter what, we need to do a partial fraction decomposition. So if we were given this, s over 2 minus 3s plus s squared, first thing we should look at is, can we factor that denominator? And we can. You factor it and you get that. So now it looks like we can break it up into something over 1 minus s plus something over 2 minus s. And both of those will look like our e to the at. So let's do that quick recap of partial fraction decomposition. So we want to write this as a over 1 minus s plus b over 2 minus s. What we do is we combine the fractions. So that's a times 2 minus s plus b times 1 minus s, all over 1 minus s times 2 minus s, finding a common denominator. And that we then gather together the constant and non-constant terms. So the constant term here is 2a plus b, and the non-constant s term, that's a negative as minus bs. So factoring out the s, we have that. And that has to be equal to this left-hand side, and we write the numerator there as 0 plus 1 times s, because we want to equate coefficients. So that means that 2a plus b must be equal to 0, and 1 must be equal to negative a minus b. So those two are equal. So we have a system of equations with a and b, and then we can solve the system by, for example, adding them together. And we get that a is 1, and therefore b, which is negative 2a, is negative 2. So therefore, this is the same as the inverse transform of 1 over 1 minus s plus negative 2 over 2 minus s. And one can always check one's work by combining the fractions together, making sure it's equal to the original. So if one combines them, we have negative 2 plus 2s plus 2 minus s is indeed s up there. Okay, so we've broken this up into two pieces, each of which is much nicer to deal with. So we have found that this is the inverse transform of 1 over 1 minus s minus 2 over 2 minus s. Let's pull out a minus sign from each of these because we want it to be s minus a, not a minus s. So this is the same as negative 1 over s minus 1, and this is plus 2 over s minus 2. Now we can break it up, distribute over the sum, pull out constants, and now each of these guys is of this form. So we have negative e to the 1t plus 2e to the 2t. So we have found our inverse transform. Now here's the first of our Laplace properties, aside from the linearity, which is how to take the Laplace transform of a derivative. This is, of course, invaluable since we'll be using these to solve differential equations. So the Laplace transform of the derivative of f, we can plug it into the definition for the Laplace transform. We have an f prime there. And what we do is we integrate by parts. So we integrate the f prime up to f and apply the integration by parts formula. And what we wind up with is the Laplace transform of the original function f instead of f prime. So we get negative f of 0 plus s times the Laplace transform of f. And instead of writing the Laplace transform of f of t, we have this shorthand notation, where we'll often just write that the Laplace transform of little f is big F. So same thing. So more compactly, we say that the Laplace transform of f prime is s times big F of s, the Laplace transform of little f, minus f of 0. Using this, let's solve our first differential equation using Laplace transforms. This is a simple differential equation. We definitely don't need Laplace for it, but we're illustrating. So here's how it works. We take the Laplace transform of both sides of the differential equation. For the Laplace transform of y prime, we use the formula that we just learned. I'll get to the general in a bit. So that is s times the Laplace transform of y minus y of 0, and that is going to be equal to 2 times the Laplace transform of y. Now, our alternative notation is just to write big F of s instead of Laplace transform of y. Just to get used to that, let's write it that way. S times f of s minus, now y of 0. That is given. It's the initial value. So one interesting thing about solving differential equations with Laplace transforms is that there isn't a need to solve the general differential equation first and then solve for the arbitrary constants. Instead, one puts the initial values straight in to the Laplace transform, which is nice. So we are given that that is 3 from the initial value, and that is 2 times the Laplace transform of y, which is big F of s. And now what we do is we solve for that Laplace transform of y. After we solve for it, we'll then take the inverse Laplace transform to get back what y actually is. So how do we solve? We'll get it on one side, so that's sf of s minus 2f of s is equal to 3. Rearranging, we factor out the f of s. We divide both sides by s minus 2. And remember that f of s, that was the Laplace transform of y. It's just alternative notation. Okay, and what that means, taking the inverse Laplace of both sides, if the Laplace of y is that, then y is the inverse Laplace of that. We can pull out that 3. We have 1 over s minus 2. And 1 over s minus 2, that is of the form 1 over s minus a. So we have 3 times e to the 2t. And amazing. That's it. That is how you solve a differential equation with Laplace transforms. You take the Laplace, you solve for the Laplace, and then you undo the Laplace. So that's a very slick tool. It converts the differential equation into an algebraic equation where we then solve that algebraic equation and undo the Laplace. Now that was our Laplace transform of a derivative. You may have noticed this. One can generalize that derivation for the Laplace transform of a derivative to the Laplace transform of an nth derivative. And this is the formula for the Laplace transform of an nth derivative. So if we're taking the Laplace transform of the second order differential equation, for example, we'll need this more general formula. So let's now solve a second order differential equation using Laplace transforms. So we take the Laplace transform of both sides. The Laplace transform of y double prime, for that we need the formula here. That is s squared f of s minus s times y of 0 minus y prime of 0 is the reading of this for n equals 2, the second derivative, and that is 4 times the Laplace transform of y plus the Laplace transform of e to the t. Now we plug in our initial values into the appropriate places. So y of 0, that is 2, and y prime of 0, that is 3, and that is equal to 4 times the Laplace transform of y, which we denote f of s, plus the Laplace transform of e to the t. And the Laplace transform of e to the t is 1 over s minus 1 by this. And now, just as before, we solve for big F of s. So we'll gather that on one side. and we factor out the big F of s, and divide by s squared minus 4, and that is our Laplace transform of y. And now we take the inverse transform of both sides. This is the stage that can be annoying. Fortunately, it's already a sum, and each of these first two pieces looks like a hyperbolic sine or a hyperbolic cosine. So those are not too bad. And then for this third piece, it looks like we'll unfortunately need to do partial fraction decomposition. Okay, so we had this, and that f of s, that is the same as the Laplace transform of y. So that means that y is the inverse Laplace of this whole thing. Okay, now we can break it up. So that's 2 inverse transform of s over s squared minus 4. Let's write that as 2 squared. S over s squared minus 2 squared. Remember that for hyperbolic sine, that just becomes a minus. For hyperbolic cosine, that becomes a minus. So that's why we're writing it that way. Now that is exactly of the form of the Laplace of hyperbolic cosine, s over s squared minus k squared. There, that's 3 times the inverse transform of 1 over s squared minus 2 squared, and then plus the inverse transform of that. We'll deal with that separately. Okay, so right now, these two guys are nice. That is hyperbolic cosine of 2t. And then is that hyperbolic sine of 2? Be astute, there's a k up there. So what we need is to get that 2 up there. So how do we do that? We can multiply by 2 and then divide by 2. Yep, so again, that was multiplying by 2 on the inside and then pulling out the 1 over 2 to the outside. So that 2 over 2 is the same as doing nothing in a fancy way. So now that is 3/2 hyperbolic sine of 2t, and then plus the inverse transform of that. So with our knowledge of inverse Laplace, these two pieces weren't that bad. And this piece, we do need to do partial fraction decomposition on. Okay, so what was left for us to find was the inverse transform of s minus 1 times s squared minus 4. We want to factor this, and s squared minus 4 is s plus 2 times s minus 2. And we can do this partial fraction decomposition in the usual way. It's just now we have 3 constants up there instead of 2 that we need to solve for, which we solve for by combining and equating coefficients, same as always. And I trust that we know how to do that in theory. It can just be somewhat tedious. I'm going to ask Wolfram alpha, and you can always use this to check your work. The partial fraction decomposition of that is that. So doing that partial fraction decomposition, we will wind up with this. And now we're almost done. Something over s minus 1, that's that. And remember, for something over s plus 2, we just want to write that as s minus negative 2. And that way it's of the form s minus a. Okay, so we have that. We use linearity. And now each of these is routine because it looks like that. And we have found the inverse Laplace of that final ingredient. So what we finally have gotten is that y, which was the inverse Laplace of this, that was our original big F of s, is equal to 2 hyperbolic cosine of 2t plus 3/2 hyperbolic sine of 2t. And then this part here became minus 1/30 to the t plus 1/12 e to the minus 2t plus 1/4 e to the 2t. And if we want, we can then spell out what these hyperbolic sines and cosines are. And we have that. And now, as a final step, we could simplify, combining the e to the 2t's together, combining the e to the minus 2t's together. And then we have that lone e to the t by itself, stemming from the s minus 1 there. And then we'll finally have our solution to the differential equation. And simplifying, what we'll get is 2e to the 2t plus 1/3 e to the minus 2t minus 1/3 e to the t. So that's solving second order differential equations using Laplace transforms. Some are nicer than others, although the method very consistently works and is a powerful technique. All right, that does conclude section 7.2. We have finished our introduction to Laplace transforms. We can now solve a number of differential equations with them. Have a great one.